To check here. Would you like to save this? Nope. And I'll see if it's going live on my channel. And then if it does, there we are. Very good. All right, we got over 13 people watching. So I am going to welcome Professor Adam Frank of the University of Rochester, a New Yorker. Are you a native New Yorker too, Adam, like me?
Jersey, just across the river.
Oh, okay. Jersey. It's the best, small price to pay to get out of New Jersey. The $20 or so that it costs.
I'm a bridge and tunnel person, as they usually call it.
No, I love it. I love it. And it's such a pleasure joining us from Rochester, the house that Kodak built, if I'm not mistaken. And we're going to talk today about searching for techno-signatures. This is Alien Month, not only on the Into the Impossible channel. We've had on Mick West, Seth Shostak, and later tonight, we will have Michael Shermer and Eric Weinstein debating UFOs. But we've also had on in the popular culture, from 60 Minutes to an op-ed you wrote in the New York Times, which is called UFOs and the Search for Alien Life, from June 6th. This is an actual, the truth may be out there, but I'm a physicist who searches for UFOs. They don't impress me, or aliens and UFOs don't impress me. Anyway, Adam, how are you doing today in my former home country, my landsman of New York? That's great. So I am going to just broadcast to the universe that we are live, and I want people to join us in the live chat for our members. I am Brian Keating, also the co-director of the Arthur C. Clarke Center for Human Imagination here at UC San Diego. And Arthur C. Clarke, as you know, Adam, was no stranger to the concepts of interstellar and intergalactic, perhaps otherworldly intelligences, natural and otherwise. So it's befitting that you are joining us in this month for a live webinar, what I'm calling the Journal Club, where we go over interesting topics by world-renowned scientists. First of all, Adam, I want to thank you so much for all the outreach you do. Can you say a word or two about what motivates you to do the prolific amount of writing, of teaching, and outreach that you do? You don't get paid for it, as far as I know. You make a little from a book, but you don't get paid for it. So why do you do what you do so well?
The love of science, right? I mean, so what, I fell in love with science when I was 5 years old, because I found one of my dad's science fiction pulp magazines. And then, that passion never cooled. And then I discovered Carl Sagan when I was, a teenager, and his writing was so clear. And you just enlivened my own sense of science's beauty. And I sort of felt like there was a responsibility to give back, to tell people about this. Part of it is just, when you think something is really cool, whether it's the Avengers or 2001, whatever your favorite pop culture, you want to tell people about it. And science is so awesome. I want to tell people about it. But I also believe, I still have that enlightenment ideal that science is one way. I mean, I think there's parts of the enlightenment we need to move past, but the sciences is a way for having a just society. It's a way to have public knowledge. So I'm kind of an evangelist of science, both because it shows you how remarkable the universe is, but it also can be a route to having a just and equitable society. So.
Yeah, and also I think the notion of science fiction, which oftentimes, as you point out in this wonderful book, Light of the Stars, which we won't talk about as much in this conversation, is more of a actual, as I say, journal club, seminar, colloquia, whatever you want to call it. I wanted to show for my viewers out there what it's like to be an actual scientist. And so I'm never going to dumb it down. I always say this is actual, legitimate, realistic, cutting edge science. Adam is one of the most renowned scientists of our time. He's also a communicator. He's written many books. I have this one in physical form, and it will go to one of you lucky listeners out there who registered. And you can still register. There's a link in the YouTube text description box. You can win this very copy. It's endorsed by some of the most renowned people around the world, from Sean Carroll, Lord Martin Rees, Kim Stanley Robinson, and Jill Tarter, who's a friend and past guest on the show. We're going to talk today about searching for techno-signatures. And this is, what we all love to do when we go to the club and we listen to the signatures of techno music. No, we want to turn it over to Professor Frank. And those of you out there, I also want to give this as an opportunity for young people to look at how a faculty member like Adam teaches. Consider applying to University of Rochester graduate school, undergraduate. this is one of the top renowned universities in the world, and the type of research that you can do in astronomy, I think, is the broadest. Would you agree, Adam? Of any type of field, you can do everything from biology to plasmas and everything in between, right?
That's what makes astronomy, astrophysics so interesting. You got to be a generalist, and so.
Yes, I love it. So I'm going to turn it over to Adam, and he will run the show in terms of giving the actual tech talk, and then we'll take questions. You can put your questions in the chat box, and I'll monitor those. And again, don't forget to take a look at the contest to enter if you want to win a copy of this awesome book written by Professor Frank, while he and I were both writing for the same publisher, Norton. This, I think, came out around the same time in 2018, and I loved that book when it came out, and I'm hoping to hear another book coming from Professor Frank soon. So Adam, take it away, my friend.
First of all, thank you for having me on. Also, I'm a big fan, as they say, of your work as well, and all the outreach you do, as well as the real science, the actual day-to-day science that you do. So we're on the same page when it comes to trying to balance doing actual science and doing actual science outreach. So. All right, so hopefully this won't take more than like 40 minutes or so, but it's a little talk about aliens. So I want to talk about techno-signatures, biosignatures, and try and wrap in also why this matters to us on the Earth. Okay, hold on. All right. So here's where we're going, a little background, or at least a roadmap. First, we're going to talk a little bit about the history of SETI because it's fascinating. Then we're going to talk about these 3 revolutions that have occurred in astrobiology that really change how we think about life outside of other places other than the Earth. Then we're going to talk about biosignatures, because you can't talk about techno-signatures unless you talk about biosignatures. And then we're going to talk about sort of this is very new, really, the resurgence in the study of intelligent life in the universe. And we'll talk a little bit about how, with the systematics that are coming out of it. And then finally, if we have time, we'll touch on how this relates to what's happening on Earth now, particularly, this amazing thing that's happening with us with climate change and the Anthropocene. Okay, so let's start where it all begins, and it all begins with Enrico Fermi in 1950, as he and 3 friends are walking to lunch, basically, at Los Alamos. And they're talking, as they're walking, they're talking about a funny cartoon in the New Yorker, which I show here, which was blaming the disappearance of trash cans on UFOs. UFOs were already a thing. They were a new thing, but they were a thing. And that got them, as physicists will, start talking about, interstellar traveling at, light speed, what was possible, etc. And then the discussion moved on to something else. And then about, 40 minutes later, after they've sat down and they're eating their burgers or whatever they're eating, suddenly, in a very Fermi kind of way, Fermi blurts out, "But where are they?" Right? And apparently everybody at the table just cracks up because they know Enrico Fermi. This is the way Fermi works. Where he will, in an instant, see the heart of a problem. And the heart of the problem he had recognized was that if technological intelligence is common, then it would probably spread from one star system to another. And why weren't they here now? Why weren't they already here? So that this was, and as we'll see, this was the beginning of trying to scientifically formulate, even though he wasn't scientifically formulating. What came out of this is going to be the first one of the first formulations of the problem of thinking about civilizations elsewhere. The next big step in SETI was Project Ozma, which was taken by the great hero of this field, Frank Drake, who was a new hire at the Green Bank National Radio Observatory, and managed to convince his colleagues that, hey, we got this great big telescope. Why don't we look for signals from other civilizations? And it's a great, very funny story, which I talk about in the book, in Light of the Stars. So they built the detectors, they did the search, they searched for, it was 4 nearby stars. They didn't detect anything, but it drew a huge amount of attention. It got national-wide attention. People were flying in to see it. And this was really the beginning of the search for extraterrestrial intelligence, the formal scientific search. Even though people have been talking about this since Aristotle, this was the beginning of a true formal search. So after Project Ozma is over, Frank Drake is kind of looking over his shoulder to find out like who's laughing at him. But instead what happens is he gets a call from the National Academy of Sciences because they want him to run a meeting on, of all things, interstellar communications. So he puts together this team of all-stars of people, that he invites, and there's 7 of them, and they spend a few days talking about this problem. And in order to basically what Drake was doing was pulling together an agenda for the meeting, and he writes down this equation, which would go down in infamy, maybe not infamy, but it would go down in history. And really what this was just his attempt to break the meeting up into bite-sized chunks. And this is the Drake equation. And let's just very quickly go over it, because you'll see what he did. He was trying to break the problem of N, how many civilizations are there out there that we could communicate with, into bite-sized pieces. This is the very essence of science. You have a hard problem, break it up into parts that you can solve. And so the first part is, in this equation, the total number of civilizations is going to equal the number of stars forming per year times the fraction of those stars that have planets times the number of planets that are in so-called habitable zone, the place where life could form, times the fraction of those planets where life actually begins, times the fraction of that life that goes on to evolve intelligence, times the fraction of those intelligences that develop technological civilizations, times what I like to call the final factor, which is the lifetime of those civilizations. So, this equation became sort of the standard way of breaking the problem up. And some people like to deride it and say, oh, it's not worth anything. But I think they're wrong. There's a reason why this equation has lasted, because it allowed us to see what we needed to know in order to know the answer to the problem. And now people have spent their entire lives working on just one of those terms in the equation. Okay, so that was the Drake equation, very important. Another thing that happens in the early 60s is Freeman Dyson, a physicist, writes a paper where he suggests that, one thing an advanced civilization might do is surround its star with some kind of device that could absorb solar energy, thereby harnessing the entire energy output of a star. And this became what was known as a Dyson sphere, and it also became sort of a standard in the discussion of extraterrestrial. So Dyson spheres, and like the Drake equation, enters into this literature of SETI. Also along those same lines comes the Kardashev scale, based on a work that a Russian physicist, Kardashev, did, where, and again, this is energy, right? So, if you're a physicist, you want to think in terms of the things you're used to, and it's, energy, momentum, etc., are going to be the quantities you think are going to be important that any civilization is going to have to deal with. So Kardashev developed this scale that would talk about the amount of energy a civilization had at its disposal, which also was about detection too, because if they were harnessing that energy, some of that energy would spill over, or you might see the effects of that energy being used. So a type 1 civilization was a civilization that could use all the power available to the home planet. Type 2 was all the power available to a star, or from the star. And of course, that's like the Dyson sphere, right? You wrap your star with solar panels and collect all the energy. And a type 3 was like the entire galaxy, 400 billion stars worth of energy you had at your disposal. So this also, the Kardashev scale, becomes a sort of standard in the discussion of SETI. And now a few years, or once we get to the early 70s, we see that Fermi's question, become formally the Fermi paradox in a paper by Hart in 1975, where what he did is he recognized that even if you were traveling sub-light speed, that the time it would take for a civilization hopping from one star system to another, leaving a settlement to become its own civilization, that the timescale it would take for this settlement wave to expand across the galaxy was much shorter than the actual age of the galaxy. So a tiny fraction is a matter. It would only take about 600,000 years for moving at 1/10 of the speed of light for this propagation wave to get across. So, for him, for Hart, this meant, he called this, so what Hart did with this this fact was he paired that fact, how fast it would take to get across the galaxy, with the fact that there's no aliens here now. We don't see any remnants of an alien civilization. We don't see any aliens now, barring UFOs. So his fact A, there's no aliens here now, must mean that there's no aliens at all. So for Hart, the fact that there were no aliens here now had to mean there were no aliens anywhere. We were the only intelligence in the universe. Now, some people tried to rebut this, including Sagan and others, to say, look, this expansion wave, it's going to stall. Maybe you're going to open up holes because of supernova. So people tried to rebut this, and we're going to see later on, this is now a new, people are starting to study this again, including my own group, my own collaborators. So that's really when Fermi's question becomes a formal scientific problem of Fermi's paradox. Now, there's another version of the Fermi paradox I want to talk about as well. Hart's version was direct. It was sort of like, why isn't anybody here now that I can see? But, Radio SETI had been ongoing for a while, and there were some people like David Brin wrote a great paper on this, saying like, well, we haven't found anything yet in the SETI searches we've done, and he termed this the Great Silence. And the
David may be watching, actually. He just emailed me to get the link to the video. So
David,
hopefully David is watching right now.
So that was an excellent paper. And so David, that was the idea that like, well, we haven't heard anything. So, where is everybody? Are we alone? And along with this came another important idea, the great filter. Well, if we don't see anything, perhaps there's a filter somewhere in evolution that keeps advanced civilizations from forming. Maybe it's early on, maybe it's very hard to form life. Maybe it's just very hard to get intelligence. Maybe it's after where we are, where like, every intelligent technological civilization blows itself up. So this great filter idea also enters into the literature. All right, then by the time you get to the 70s and such, you're now getting the second generation of SETI pioneers. And SETI had started to get some steam. It was still not mainstream astronomy, but it started to get steam. And so there were the second generation, people like Jill Tarter, Woody Sullivan, who was an astrophysicist at the University of Rochester, and was he was the first guy I ever really talked to about SETI. Woody's great, I love him. As Seth Shostak and others. And so, now SETI is continuing to build up steam, and it's actually SETI, it's going to be SETI researchers who are going to push the development of cameras or techniques to find exoplanets. They were absolutely instrumental in that push. Now, the important thing, though, to understand is at this time, people were SETI, what I'll call classical SETI, was really very much focused on radio beacons, right? The idea that somebody was, sending out signals that were meant to be found. So the emphasis on radio was because radio is more the detectors would be more sensitive over large distances. Longer wavelengths also meant that the radio waves could propagate through dust and such. And the beacon part was because, the SETI is a very challenging problem. You don't know where to look. You don't know when to look. You don't know what frequency you're supposed to be tuning your radio telescope to, and you don't know exactly what to look for. So that's why beacons made sense given the constraints that you had at the time. And of course, this is what exactly, in the famous movie Contact, which the younger generation may not know, but you should watch because it's still super cool. So beacon SETI was sort of the emphasis for this up until the second generation. But then comes the death of SETI, the death by what we call the Giggle factor. What happened is, the first time this happened in 1978, Senator William Proxmire, NASA was about to fund a big SETI project, but Proxmire awards that project what he called the Golden Fleece Award, the fleecing of taxpayers. And literally, NASA was not allowed to fund SETI from that. So that happens, and these people, it calms down for a while. And then in the 1990s, again, NASA tries to fund some SETI programs. And there's another big uproar. These are politicians trying to score points. Oh, we're not going to search for little green men. And I got a couple quotes up here that are not worth going into. But this pretty much, at this point, NASA's like, all right, look, we're done. We are not going to risk. NASA's got to go to the Congress for its funding. It was too hot a topic. They kept getting beaten up. So, it's understandable why they kind of backed off from it. But then what, of course, happens in the 90s is there's the Mars rock that is found in Antarctica, which seems to indicate that maybe there was fossil life on Mars. Now, we don't really think that's true anymore, but it started people really thinking about astrobiology in the solar system. And then, of course, as we're going to talk about, exoplanets were discovered. So as I say, Congress wanted to kill SETI because it worked for getting votes, but nature and science had other plans. So I want to talk about 3 revolutions that brought astrobiology back into the fore. And of course, astrobiology is the study of life in a cosmic or in particularly planetary context. So the first was the discovery in 1995 of exoplanets, planets orbiting sun-like stars, not pulsars, because pulsar planets were discovered earlier, but stars that you could imagine having life occur. And as I said, you can see Aristotle and Democritus beating each other up over the question of whether there were other planets orbiting other stars 2,500 years ago. And in 1995, the question gets definitively answered. That's pretty amazing. And so then things like the Kepler mission just starts finding planets wholesale, exoplanets wholesale. And so, now we have lots, we know about 4,000 exoplanets for sure. And we can do the statistics of them. So we know about, really, in some sense, we know even more about even more exoplanets. And we found lots of exoplanets that are potentially habitable or in the right place where, water, liquid, you could pour liquid water on the surface and it would just sit there if you had an atmosphere. So we've learned quite a bit. The second revolution is we have now sent robot probes to every type of solar system object out there. Right? Every planet has been visited. We visited asteroids, we've visited comets, we've visited, you name it. And in particular, Mars is entirely inhabited by robots. Mars is a robot planet. And they've been those robots have been wandering around taking amazing pictures like this one, right? If I showed you this picture and didn't tell you where it was from, you might say, oh, that's Tunisia, that's the desert somewhere. But no, it's Mars. And by studying these other planets in our solar system, in detail, we've learned things like Mars was probably a blue world once. Maybe not for very long, but we now have conclusive evidence that Mars had a lot of water on it for a while, rushing water. There's a great example of climate change there, right? Mars used to have enough, it'd be warm enough and have enough atmosphere to have liquid water on its surface. Now it's a frozen, dry hell. So there you go. Now, the third revolution is embodied in this picture. And when I show this picture, I like to ask people, which one of these is the Earth, right? And so you can look at that for a minute and think about it. And of course, it's a trick question because they're all Earth, right? Earth, what we now have learned from Earth's study of Earth, its deep history, is that the Earth has been many planets across its lifetime. In the beginning, it had a molten ocean during the Hadean period. And then later on, it was a water world. Once it cooled enough, water condensed, and there really weren't continents yet. There were sort of proto-continents. So it was a water world. At some points, the Earth has been so hot, there's been no ice anywhere on it, except maybe at mountaintops. So it was a jungle world. At other points, it was all ice. It was almost entirely glaciated to be a snowball world. And then, of course, here's our happy version of the Earth now. But unfortunately, in about 1 billion years, as the sun warms up, Earth will become, the oceans will boil away. And cash your Bitcoin in now, man, because it's not going to last, okay? So from these 3 revolutions, even though we haven't discovered life anywhere else yet, we have learned so much about how life and planets can interact that we are now prepared. We know how to search for life in the universe. So, okay, what does the exoplanet revolution and these other revolutions change about SETI and thinking about intelligent life in the universe? Well, the first thing is we now have new data for the Drake equation, right? So remember, this is the Drake equation. When Drake wrote this down, only the first term, R sub star, the rate of star formation, was known. Now we know for sure, really nailed the statistics of F sub P and N sub E. And what we know from these, this is an amazing fact, every star you see in the sky pretty much has a planet, probably a family of planets. And if you count up 5 of them, one of them is going to have a planet in the right place for life to form in the habitable zone. So that's new information, and you can use that. Woody Sullivan and I use that to try and rearrange the Drake equation to see, well, okay, now what can we say about the probabilities, et cetera, for life. And really what comes out of this is we now know that in the observable universe, there are 10 to the 22 planets, habitable zone planets, not just planets, but habitable zone planets. That's 10 billion trillion planets. So if you just want to do a simple frequentist kind of model for the probability, it means that, okay, the only way that we're alone in the universe is if the probability of forming a civilization per habitable zone planet is less than 1 in 10 billion trillion. Okay, that's a pretty small number. Now, of course, you can say, well, what do I judge it against? Well, you can judge it against other, people have been arguing about this for a while, and that number is way smaller than anybody would have said beforehand, right? So people, what I mean by this is that people who in 10 years ago, 20 years ago were thinking that they were pessimists because they had some number, for this, how unlikely life was. The actual number turns out to be so much lower than that they were actually optimists. They would have said there were no civilizations in the universe. And now that we know what this kind of probability should look like, they would actually have predicted millions, billions of habitable, or not habitable, of civilizations. So we can go back into this later if somebody wants to. But that's one way in which this new information actually changed SETI. But more than that, what really changes is that now, because of exoplanets, you know exactly where to look, right? And you know exactly what to look for. I'm not just randomly choosing stars. I'm choosing a star that has a planet in the habitable zone. I'm going to stare at that guy for as long as possible. So let me talk a little bit more about that, because that brings us into the idea of biosignatures, right? So this is just remarkable. I mean, we could go on for hours about how unbelievably remarkable this is. One of the main ways we detect exoplanets is when the exoplanet, if the orbit is right, that the exoplanet passes in front of its star. It does a little mini eclipse of the star. And there is a moment there when that's happening. So here's a diagram of this. You see the star, that's the yellow. You see the planet, that's the black. But this little white halo, that's the atmosphere. If the planet has an atmosphere, there is going to be a brief window when the light from the star passes through the atmosphere. And as we do all the time in astronomy, we can use the imprint, the fingerprints of the elements that absorb light in that atmosphere. Usually we do it for interstellar clouds, but now we can do it in this exoplanet's atmosphere to tell what's in the atmosphere. So we can get markers for what kind of chemicals are in the atmosphere. And we believe there are certain chemicals that would or molecules that would only be in the atmosphere if life was there. The example of this is oxygen. The only reason there's oxygen in the Earth's atmosphere is because of life. Microbes basically, pardon my language, farted oxygen into the atmosphere to create the oxygen we breathe today. If life disappeared from Earth, the oxygen after a relatively short time would all react away and be gone. So we believe that oxygen and methane, both in the atmosphere, could be a very good biosignature. But people, there's this huge effort searching for, trying to characterize, okay, what biosignatures should we look for, And so here's actually the Earth through time. This is age, if you go down here. And these lines here are the concentration of various chemicals in the atmosphere. So if you just look at this diagram on the left, and go down, let's look at oxygen. You see that in the beginning, 4 billion years ago, there was hardly any oxygen. And then over time, the oxygen rose in what's called the Great Oxidation Event, and then rose again to the level that we have now, right? And there's other elements in here that you can see changing over time. So that means that if we looked at a planet, if someone was looking at us billions of years ago during what's called the Archean phase, and they looked at the spectra, so this is the intensity of radiation versus wavelength, they would see a bunch of dips, a bunch of chemical fingerprints from various elements that would tell you that, oh yeah, there were some early life there. By the time you got to what's called the Proterozoic Earth, some of those had changed. You got new biosignatures in it, and the modern Earth has a whole range of things that if you could observe it, you would say, wow, for sure that planet has a biosphere. That planet has a robust, set of network of living things that have completely changed the planet. So over the past 15, 20 years, people have really dug into what we could call biosignature science. And here's this great paper, if anybody's interested in it, that has like some of the superstars of this field. And, you know, people are really thinking deeply about, well, how do we go after biosignatures? You know, first of all, what produces life? What, you know, how could a dead planet fool us into thinking that it had biosignatures? No matter what, our data is always going to be somewhat limited. How do we interpret limited data? And how do we quantify how certain we are if we think we find a biosignature? Because this is going to come back later. I want to say, you know, if somebody makes a claim that they found a biosignature, you can bet they're going to get their butts kicked by other scientists, as they should, to see, you know, the standards of evidence are going to have to be very high. You can't claim that you've detected life unless your evidence is going to be extraordinary. And, you know, people are preparing for that. So, okay, so biosignatures are about, I'm sorry to say this because I love microbes, but it's about dumb life, right? What about smart life? Well, that's techno-signatures. So remember that, you know, sort of NASA had gotten gun shy from doing anything, really diving into intelligent life because of what had happened. But then in 2018, remarkably, Congress actually added to the budget a requirement that NASA should study techno-signatures. And so NASA then called a meeting in Houston, and I was lucky enough to be at that meeting. And everybody was like, oh my God, you know, like NASA's asking us, what should we do if we were going to study techno-signatures? And it was a great meeting. It was so much excitement and ideas were just flowing everywhere. It was one of the most fun meetings I'd ever been at. And out of this came this report that Jason Wright and others spearheaded. And we all contributed, but Jason is the man. Was the first author on it. But like I said, there were also women, of course, you know, as well. So it was, you know, an amazing group of people who came together to do it. So you can read that report. One of the things that came out of that was systematic thinking. It was the beginning of systematic thinking. So Sophia Sheikh, who is, you know, a graduate student, but what I consider, you know, she's, you know, one tip of the spear of the next generation of SETI or techno-signature thinkers, came up with this idea after listening to the talks about the idea, well, we need figures of merit. We need some way of judging. If I propose a techno-signature, how do we know whether that's worthwhile going after? And so she proposed this figure of merit, nine axes of merit. For example, can the search only be done in the far future, or can it be done now with existing telescopes? Will the techno-signature be short-lived or long-lived? Will it be ambiguous or unambiguous, et cetera? So, you know, we can go down this, but we don't need to now. The main thing was, it was the beginning of starting to have, bright young scientists like Sophia, you know, to creating a community to really revitalize, how do you think about this problem? And especially now that you've got exoplanets to look at, how do you think about this problem? How to be systematic about the scientific search? And then, remarkably, NASA funded a techno-signature search. So we put together a team. I was the PI on this one. And we asked for 2 years of funding to categorize atmospheric techno-signatures, and that grant was funded. And we're now putting in these are the people who are part of, we're about to renew it. I think we've been very successful. I'll show you some results. I'd like to argue we were successful, but this was a watershed moment. And now there's been a few other techno-signature grants that have been awarded. So it's great. The ball is beginning to roll. And then there's also Breakthrough Listen, which funded to the tune of $100 million, the renewal of radio SETI as well. So, you know, it really feels like, something has changed. So let's talk about techno-signatures. What are examples of techno-signatures? Particularly the techno-signatures that are going to be associated with exoplanets. So I'm going to run through these quickly, and then I'm going to talk about them a little bit more. There are the possibility of seeing city lights or heat islands on planets. There's the large-scale deployment of solar panels on planets or moons. There are atmospheric pollutants, things that shouldn't show up in an atmosphere unless there's industry going on. And then there's everyone's favorite, orbiting megastructures. Who doesn't want to say the word orbiting megastructure? Okay, so this figure actually shows, gives you a little graphical representation. This is a big grant that we put in, an ICAR grant to NASA that Jason Wright spearheaded. It didn't get funded, but hopefully next time we'll put it in again. But here you kind of see everything. You see the city lights, you see some orbiting megastructures, but let's go into it in more detail. So alien megastructures is the idea. It's kind of like a Dyson sphere, but instead of a Dyson sphere, think of it more of as a swarm. You've got lots of large orbiting objects orbiting the star, perhaps collecting solar energy. Now, the amazing thing about this is we almost thought we saw one, right, with Boyajian star. This is the transit data for Boyajian star, and you see it's if you know what transits for planets look like, this doesn't look like it at all. It had all of this irregular, short drops in the light, making it look like the star was being orbited by a bunch of blobs. And so when when they wrote the paper on this, they gave a bunch of possibilities, most of all of them natural, except the possibility for alien megastructures, which of course made huge news. Everybody was excited about it, and we all knew that probably that's an extraordinary claim. It's probably not what's going to be what's happening, but it was the beginning of being willing to say, getting past the giggle factor. Look, of course we have to consider this. We'll probably rule it out, but at some point we may not be able to rule it out, right? Okay, so alien megastructures, one type of techno-signature. City lights and heat islands. So there are telescopes on the drawing board now that may be able to map the features of an exoplanet for looking for just even continents, right? So this is work by Berdunya and Kuhn, where this is, look at this. This would be the map. This would actually be the map of a planet with its continents. And with things like the extremely large telescope, you would be able to recover a version of this. You'd actually be able to make out, the basic contours of the map. And if you're using infrared, if there are city lights, if there are heat islands from industry, you might be able to make those out too. So that's really exciting. I mean, this is obviously next generation kinds of stuff. But even with JWST, there was a recent paper that showed that, if the city lights are in a narrow band, if they're emitting like sodium lamps, where it's a single frequency, you might be able to see them. So even new technologies that are going to get launched soon, you might be able to see them. Another possibility is, look, if you cover a lot of your planet or a moon with solar panels, Lingham and Loeb showed that you would be able to, you would actually see the imprint of all of the solar panels in the reflected light. And regardless of which kind of material you use, they would all imprint a signature in the reflected light. This is something that came from our group that we just did. This was Jacob Hock Misra led this effort. And this was, I'm really excited about. We looked at chlorofluorocarbons, right? When the CFCs, that's the stuff that, damages the ozone. But it's a chemical that, it's very hard to imagine that nature would produce CFCs on its own. It's really a unusual, kind of molecule. And so what Jacob and Ravi did is they ran climate models where they put in various levels of CFCs into the climate model from exactly what we have now up to 100 times more. They ran the model, allowed everything to sort of equilibrate, and then they took spectra. They took synthetic spectra as if they were observing it from a distance using the JWST or using more advanced telescopes that are on the drawing boards. And what they found was, and you can see this here, these dotted lines here, the blue line, the red dotted line, the black dotted line, the signature of the CFC stands out. It's just it's clear that it's there. In fact, what we found was that with the JWST, we would be able to detect Earth levels of chlorofluorocarbons using using the JWST. This is a milestone for SETI, because what it means is that using Earth-based technology that we have now, we would be able to detect another Earth. Now, this was for, I think it was the TRAPPIST system that we were looking at. And I won't go into the detail in this line. Let me just note again, talking about standards of evidence, no signal is considered to be a detection of anything, whether it's particles, the Higgs boson, or something like, a chlorofluorocarbon in an atmosphere, unless you get above a signal to noise ratio of 5. That's what that. So anything above this would be a detection. And what this red line here shows you, that with just 100 hours of, in this case, this was the Origin Space Telescope, with just 100 hours of Origin Space Telescope time, you would be able to you'd be able to find, you'd be able to detect CFCs at Earth concentrations. That's down here. So it's really remarkable. And in fact, it would require less time than a biosignature. There's some biosignatures that would take longer time. So this was really, this is going through refereehood now. Hopefully it'll survive the referee. I believe it will. But this really kind of shows you where we're at right now. We're really starting to, start running in terms of characterizing what possible techno-signatures to look for, how to look for them, what their detectability is, etc. Okay, so let's talk a little bit about other kinds of systematic thinking about techno-signatures. Because that's really where the field is. We're now, since we're just beginning, we have to do more than just propose techno-signatures and characterize them. We have to ask ourselves some basic questions, like what is the expected age of a civilization that we might likely detect? Is there really a Fermi paradox? How common will techno-signatures be? What is their lifetimes? So let's just talk a little bit about this briefly. So there's been this belief in general that what you might call a prior. People sort of have this belief that, well, there will be fewer techno-signatures than biosignatures, and in general, they're going to be short-lived. And the reason people usually sort of feel this intuitively is because, well, you figure the Earth's biosphere has been around 4 billion years, but the techno-signatures just popped up, right? So there's sort of the sense of techno-signatures, they're going to be shorter-lived. But that's really not true when you think about it. There are two papers. Well, there's this paper that Balbi and Surkovic did. Longevity is the key to the search for techno-signatures. And right now, our group is, right in the midst of writing a paper called "The Case for Techno-Signatures: Why They May Be More Abundant, Long-Lived, Highly Detectable, and Unambiguous." And the reason for this is that techno-signatures they're freed. They can be freed from the biospheres which produce them, right? A technosphere, meaning if you imagine a biosphere is the sum total of life, the technosphere is what an intelligent civilization, how it would wrap the planet in technology, like we're doing now with our satellites, etc. But the thing is, a technosphere is not a techno-signature, right? A single civilization could produce, I write 10x here, meaning fill in your x, could produce millions, billions of techno-signatures. Imagine that a civilization sends out probes, to go explore the universe. Every one of those probes is a techno-signature that could be detected by us. It's going to be sending signals back and forth, that we might be able to detect. So, a single civilization can produce many, many techno-signatures, and each one of those techno-signatures could have enormous lifetimes. The civilization could die after 1,000 years, and the techno-signatures could go on for another 10 billion years. Who knows, right? I mean, we know. It just depends. If we were to coat the moon in solar panels, it would take and we died and we disappeared, the reflectance, that would show up for quite a long time. I mean, the only thing that would destroy that was was micrometeorite impacts on so really, there's arguments to be made that techno-signatures may be more prevalent, more long-lived than biosignatures. So the two aspects are very complementary, and the techno-signatures don't need to be tied to the species that created them. They can be freed from them because that's what intelligence and technology do. All right, to conclude here, I've got another 4 to 10 minutes. Let me just talk about the Fermi paradox again. The first thing I want to say is there is no indirect Fermi paradox, right? So the idea that of the indirect Fermi paradox is we looked and we haven't seen. But in fact, we haven't looked. People have this idea that people are looking for intelligent life. Astronomers every night astronomers are, turning their radio telescopes to the sky looking for signatures of intelligent life. There was never any money to do that. So Jason Wright and collaborators working off an idea from Jill Tarter actually calculated. They looked at all the SETI searches that have ever been done and calculated how much of the parameter space that needs to be searched has been searched. And if that parameter space was an ocean, the amount that we've actually looked at was a hot tub. So if you looked at a hot tub and didn't find any dolphins in the hot tub, would you then say, there's no dolphins in the ocean? So as of right now, there is no indirect Fermi paradox. We just have not looked well enough to really say anything about the prevalence or lack thereof of intelligent life. Now the that should be Fermi. The direct Fermi paradox, the one about why didn't they show up here and create a civilization that we should have evidence for? Well, that's a little bit harder. And my group, led by Jonathan Carroll Nellenbach, along with Jason and Caleb Scharf, we built some simulation software to do this. And here's a model that we ran where that white dot there is going to be a single abiogenesis event that's going to create life, which will send probes out. And here you're going to watch the galaxy. So the blue are stars. And at some point there you go. That's the wave. That is the settlement wave. And you see that it very quickly spreads across the galaxy. There's really no way. And we played with this, we had the computer technology to be able to really do what are called agent-based models of this. And it turns out there's almost no way to hold that wave back. So, in that sense, the Fermi paradox, the direct Fermi paradox, is more of a problem. However, what nobody ever considered was after that wave passes, you're now in a steady state, right? So you should have a steady state fraction of habitable planets that have a technological civilization. But if civilizations don't last forever, and there's no reason why they should, then that changes things. That means you're going to have civilizations die and then have to be reseeded, et cetera. So here is a simulation that we did where we had a finite lifetime for the settlement, and each of those different colors is a civilization and its daughters that are being produced. And what you see is here, depending on the parameters, you get pockets of civilization and settlement happening. But because the civilizations only last 1 million years or so, they don't spread everywhere. And it depends on how the stars are moving relative to each other, the density of stars. But in this case, you can have that settlement wave have passed over, but you can still have places in the galaxy, perhaps us, where there just hasn't been any civilizations for a long time, or ever, So that's actually, I think, a very interesting point. And it's, just shows you how the revitalization of the entire SETI debate, things that were talked about a long time ago are now being revitalized because we have the capacities, the computer technologies, et cetera, to study them. All right, so what does this mean for us? So we know that we're in the midst of the Anthropocene. Human beings are now the dominant force geologically in terms of shaping the behavior of the what we call the coupled Earth systems. And so, one of the things that you can really ask is, as we start thinking about other civilizations, how does that reflect back on what's happening to us now? Because clearly, climate change in the Anthropocene could be terminal for us. Human beings aren't going to go extinct, but we could put, this kind of global civilization, this project of civilization that we've been at for the last 10,000 years, it could put it out of business, perhaps for a very, very long time if the climate really changes dramatically. So, one of the questions that comes from thinking about this is, as I like to call it, the astrobiology of the Anthropocene, and this is what my book, The Light of the Stars, is about, is it allows you to reframe what's happening to us right now in terms of, in general, asking, what are the trajectories of civilizations, right? Are there rules for any civilization that forms anywhere? Are there rules for the development? Because in some sense, a civilization is just a kind of a machine for harvesting energy. It harvests energy from the planet, and it uses that energy to do useful work, which is to do the things that a civilization does. And the second law of thermodynamics tells you, look, man, when you do that, you're going to generate waste. You're going to generate entropy in lots of different forms. And that, may set rules for you in terms of what is possible for the evolution of planets. And it may be that everybody has an Anthropocene, right? And the smart civilizations are the ones that recognize it and change their behavior, learn how to come into some kind of equilibrium with their biospheres. And the dumb ones are the ones that are like, it'll be fine, don't worry about it. So yeah, which category do we fall into? Time will tell. And then with this, one of the things I think that's interesting about this is how it changes. Remember the Kardashev scale? Really changes how you think about the Kardashev scale, right? Because the Kardashev scale, for planets at least, the type 1 civilization was a civilization, it was only based on energy consumption, right? A type 1 planet would use all the power available to it from solar energy. But this was typical 1960s kind of white guy thinking about planets, right? It's like, if I have enough energy, I will rule my planet. But what we learned from the Anthropocene was that, planets, you got to be careful with that, right? It's the planets have their own ways of doing things, right? You can't bring a planet to heel, right? So I call now, when I think about type 1 planets, I think of them as planetary brutalism. They very much came out of that moment, that, like I said, sort of emerges from the thinking in the Enlightenment that planets are just dead things. Life is just, a bunch of atoms doing whatever they're doing. They really didn't understand the complexity of life. And this is something we have to learn, in general. We have to learn from all the other cultures on the Earth that there's other ways to view life and the intricacy of life as a network. And this, so you can't bring planets to heal, but you might be able to bring a plan to them. And I'm not going to go into this, but there's a paper I wrote about the idea of thinking about how, what I called the 5 classes of planet, really thinking about entropy, right? I think entropy and dissipation are a critical way of understanding planets. And any planet that's long lived is going to have solved their Anthropocene problem. And that there may be, rules for that both we have to learn and may be useful for searching for planets. Okay, my last few minutes, finally, UFOs and UAPs, right? So as Brian noted, it was really only a few weeks ago, I wrote an op-ed for the New York Times. Now, I don't get to choose the title, but actually this title I was okay with. I'm a physicist who searches for aliens. UFOs don't impress me. And what I really meant was the data associated with linking UFOs to aliens, to exo-civilizations. Come on, we're just, any claim about alien life has to have the same standards of evidence that my colleagues and I are going to be held to when it comes to techno-signatures. So there's no free ride that comes here, and that data isn't there. So let me state very clearly, though, the UAP stuff, the unidentified aerial phenomena, it's definitely of interest. There's some, interesting stuff there. It should be studied openly. It should be studied scientifically. I'm all in favor of that. Right? Okay, so don't box me into some people, because really after my Twitter, I got on the UFO Twitter's radar because of this, and it was not fun. There were some really cool people. Yeah, right. There's some, people who were, really cool, and there were other people who were just like, it didn't matter, no investigation was ever going to show that UAPs were not associated with aliens. But again, it's about standards of evidence. I just want to leave you with this, what I call the hierarchy of extraordinary claims, right? Because this is the way it sort of works for the claims of UFOs being associated with aliens. Like, okay, the claim that they want us to believe, people are like, yes, absolutely, UFOs are aliens, is that, so the claim is we are being visited by advanced alien life that can cross interstellar space, but somehow can't manage to stay hidden, right? So, all right, that's an extraordinary claim. There's huge amounts of extraordinary claims there. But what those people have to understand is that, I can take one step back and I still have an extraordinary claim. We're being visited by an advanced alien life that can cross interstellar space. Well, that claim would require extraordinary evidence. And I can take another step back. There are advanced alien life. There is advanced alien life that can cross interstellar space. We don't know that interstellar space can be crossed like by biological creatures. I mean, it's just, the distances between the stars are incredible. So that itself would require extraordinary evidence. But I can take a step even further back. There are advanced alien life, or there is advanced alien life. That would be a game-changing, monumental find, right? That requires extraordinary evidence. And then finally, all the way down, there's life. There's life in the universe. That itself is so remarkable that it requires extraordinary evidence. So like the idea that you can just jump this, somehow with a bunch of fuzzy blobs and personal testimony, we're going to just, so like I said, study it, get a data set that's worthwhile, and then we can see where it leads. But as of right now, that is just too large a claim using the data you have to be able to make. All right. So I just want to end by noting, wow, Carl Sagan. When I wrote the book, Carl Sagan was everywhere. I couldn't believe how many places Carl Sagan showed up in, not only thinking about aliens, but thinking about Earth history, planetary science, you name it. It was just remarkable. So I just want to, mad props to Carl Sagan.
Yeah, he's one of the few, although someday we'll have one for you, I'm sure. Adam will have a finger puppet. Yes, and I'm delighted to have, and someday I'll put links to my interview with Andrewian and Carl's daughter, Sasha Sagan, which were highlights of my Into the Impossible career. He is certainly a hero to millions around the world, maybe billions and billions, as he would say.
Billions of people. All right, so that's it. Thank you very much for your time. I appreciate it.
This is wonderful. So we got a huge host of people, over 100 people watching live, and many will watch later, but you snooze, you lose. You have to be tuning in if you want to catch things live and ask questions. We have a bunch of questions, Adam. First of all, thank you so much. That was really fascinating. I really believe that you and your colleagues are some of the most innovative thinkers. And one thing to note that gives me hope is that, a few years back, trying to propose that a professor should be hired at a major university like University of Rochester or at UC San Diego would have been laughed off. And we have Professor Shelley Wright here, who is one of the foremost leaders in the nascent field of looking for optical signatures from SETI instrumentation. I hope to have her on the podcast once we can meet in public and don't have to wear masks or meet in person, but hopefully that'll be soon. She's a good friend, amazing scientist. Look for that soon. She has a TED Talk, actually, that you can find where she was in a prison, I believe. But that shouldn't stop us. I have a question just while people assemble. I want to ask people to leave your questions in the live chat if you're watching live. And if you catch us afterwards, you can leave a question in the comment section. And then Adam and I can maybe go back and answer those questions later. But for now, I always have a question. This is the 60th anniversary of the Drake equation. Actually, Frank put it together in 1961. I'm hoping to have him on the podcast. That'll be great, fun. And, I always think of that as an equation, quote unquote, and that, if one of our students, one of our brilliant undergraduates in Rochester or San Diego hands in a paper and it's got a number and there's no uncertainty, there's no error analysis, there's no propagation of errors associated, how would you handle that? In other words, is it a paradigm? Is it actually an equation? Is it just kind of a framework to think about things? Because as I have often said, this is not the way that you and I spend our days looking at the error analysis, not the actual average value or expected value.
Yeah, it's a framework, right? It's not a law of nature. It was a way, and that's what made it important. So I understand when people are like, you can't take this thing too far, but you can use it. It was always a framework, as Jill Tarter says, for understanding our uncertainties. What we don't know. It was a way. It was a way of breaking the problem up rationally, so that you could focus on individual pieces. So yeah, it's not. People shouldn't take it for more than it is. It was a brilliant formulation of the field. It was, it laid out how the field should be done. But mathematically, there's only so much that you can do with it. There's going to be other ways that you're going to have to think if you want to really derive. You want to derive quantitative results. There's other things you're going to have to do: Bayesian statistics, other kinds of approaches.
So, a question from one of my audience members, Optimus Phoenix Prime. So this is a transformer in Arizona, presumably. Optimus is asking, do you expect that people would travel? Do you expect that you would have alien artificial intelligence? What do you think is more likely to be in the actual zeitgeist, the kind of floating around and so forth? What would be most probable, assuming that they could make this huge traverse across the Erie Gap, as an Erie silence, as Paul Davies has said on the show?
That's a great question. And, so much of it depends on sort of, what's possible with technology. I'm not a great believer in, the idea of downloading your consciousness into machines. I don't think we really understand consciousness anywhere near that. But it does make sense that you're going to send machines, just, and then send signals back because the distances are so vast. I love thinking about, as much as I love warp drives as much as the next guy, but I'm always interested in what happens if you are limited to the laws of physics we understand now. So there's great science fiction by Alistair Reynolds, his I can't remember, Revelation Space, where everybody has to travel. They use hibernation to move around and such. So a lot of it just depends on the technology that is possible. But if I had to guess, I would think that, yeah, in general, you're going to use, you'd use robots because it's just, it's much easier.
Yeah. Andy Weir, who is a recent guest on the podcast, has a new book, Project Hail Mary, where he envisions an encounter with an astronaut who wakes up after hibernating himself for many, perhaps decades or more, to save not only planet Earth, but the observable portion of our universe. One of my good friends and listeners, loyal listeners, Nuno Maraco from Portugal, he's saying, would they send a program? In other words, would they send kind of like inverse Independence Day, where we upload on a US, luckily they had a USB-C adapter on the freaking spacecraft, but luckily, but would they send a program? Would they send something to do something rather than just like, we're here, a message? Would there actually be, a blockchain? Would it be something that you could actually do something with, that would be observable and decryptable even from the background that otherwise would appear as noise?
I think that could be very hard. One of my favorite movies, science fiction movies, is Arrival, right? Because, Arrival starts off with, they send two people in to talk to these aliens. One is a physicist, a kind of Carl Sagan physicist, and the other one's a linguist. And the physicist is like, I'm going to show them pi, and we're going to learn each other's math, and then we're going to be able to talk to each other, which has been the standard trope. And it fails miserably, right? And it's only the linguist who, understands how language actually works, who's able to develop communications. We just had a lovely talk. We have a regular series, a techno-signature series that Robbie Kaporapu runs. And today we had an anthropologist talking to us. And it's just the idea of how different alien minds could be. I doubt seriously that there's going to be this easy exchange of, programming and everything. I mean, I think it would take a long time, if it's even possible, to really decipher, the languages and such. So I don't think they could just send a program and we'd be able to upload it. I mean, there would be a lot of difficulty with that. Fascinating idea. Alien minds, fascinating idea.
The next question comes from a young and up and coming scientist by the name of David Brin, here at UC San Diego, PhD.
He's going to do something with his life.
Yes, I think he's an up and coming. Yeah, I think we better watch him. So he talks about how in a 1983 paper, he talked about the lifespan of colonized star systems and their settlements, and whether or not that wave of colonization might burn itself out. If you do the Volterra equation and you don't put any limitation on the amount of prey, the predators grow unbounded. Can the same thing happen in your galactic, wave, that it can basically run out of control if you don't put on some boundary conditions in terms of, how much actual energy it can be extracted, how many, beings would be there, I guess is the sense of his question.
Well, basically, we do that. So this is an agent-based model. So the nice thing about this is it's not differential equations. It's algorithmic, not not analytical. So really you just relied on the, now of course there's assumptions about, each agent, an agent is a settled system that has a certain time to send the next one out, next probe out. So there's a list of parameters associated with it. But really, we didn't see anything that could stop the settlement wave. It would sweep across. What could happen is, depending on, like, say, the probe, how far your probe can get before it breaks, right? So if that's short, then you'll have lots of settlement in the center of the galaxy. But as you get to the edges of the galaxy where the stars, the interstellar distance is larger, then that can sort of slow down. But Jason Wright's great insight was that the halo stars, you've got these stars from the halo that are just on these plunging orbits, that they, a civilization could, wait for one of those to come through, jump on one, and then, ride to an entirely different part of the galaxy, and then start the settlement wave again. So we just found that it was, and we tried, right? It was very hard to stop that settlement wave.
Yeah. So another question is coming from a listener by the name of Prince Charming. That's pretty cool. Shout out to the royal family. Is it possible to detect Nightside lights on exoplanets?
Well, I think this is one of the great frontiers. And there was just a paper by Avi Loeb and a collaborator that sort of showed, again, that if it was that even JWST, if you had lights that were emitting, all of their energy in a single wavelength, it would be possible to detect that. And then also, as I said, with this next generation of telescopes, where we actually might be able to get some mapping of surface features, yes, you would be able to see, you have the possibility of seeing it. So, as I always like to point out, this is a long game, right? I mean, the science, as I always like to say, science is very exciting, and it's also unbelievably boring, because, to find out anything extraordinary takes incredible amounts of work. And so, it's going to take 10, 20, 30, 40 years to get this data. But remember, this is the first time after 2,500 years we're going to have data. We're not just yelling at each other anymore. We're going to have data relevant to this question of life and intelligent life in the universe. So all of these things are now becoming possible, and we're just setting sail. We're getting in the boats and we're heading off, starting this adventure.
Yeah, one of my listeners, is loyal listener Andy Oates, is asking a question I get in different forms. In other words, maybe the reason that we're not seeing them or any evidence is that they're using such advanced technology, physics, ignoring the Tic Tacs and other sightings and bokehs and stuff like that, but actual, the answer to the Fermi paradox is just that they're using such advanced technology that they have no reason to, we have no reason to expect we could even interact with it any more than an ant colony could understand, SU3 cross SU2 cross U1.
Right. That's a good point. And it's possible, it's entirely possible. That's just, and what we just, if after, this is in some sense like what's going on with dark matter right now, right? We're now, sort of well into searches for dark matter. People are not finding anything. At some point, you get, you reach the point where you're like, okay, everything we understand about the, weak interactions, that may just, tells us that, okay, we've explored all the parameter space. And then you have to go somewhere else in terms of your thinking about this. And that may be if after, 200 years of searching, we didn't find anything, we'd either be left with there's nobody out there, or we're going to have to really rethink about how we search. But the nice thing is like there's certain laws of physics, like the second law of thermodynamics. That's really hard to get away from. I just, there's a reason why the patent office does not take any perpetual motion machine patents anymore.
Yeah, I got the last one in. I slipped the last one under that goalpost there. A couple of more questions here from the brilliant into the impossible audience. There is no more brilliant audience in all the world or the known universe, as far as we know. So there's a question. Is there a possibility, Nuno is asking again, that maybe they're staying away from us, they're avoiding us, some aliens, and that's the reason the Fermi paradox is answered in the negative, because they know we're violent and that they see everything we've done, and maybe before you answer that, Adam, I'll take a digression because I know you're capable of answering all these questions. What do you think would happen the day after you or your colleagues were successful? Let's do a Gedanken experiment. You succeed, alien biosignature, techno-signature, what have you, whatever form you like. It could be lights, it could be global warming type phenomena. And you the next day, because there are some that say, and it's 10 sigma, confirmed, peer reviewed, published in the New York Post and the Nature journal. So we can really believe it. You can't believe it until it's published in
Nature. Yeah, right.
So my question to you is, what do you think would happen the next day? In other words, and that'll dovetail back into Nuno's question, I promise.
I think it would be profound. I think there would be, the next day, the next year, the next 10 years, the recognition that we were not alone. I think, even if we weren't getting messages, I still think it would revolutionize philosophy, religion. We'd have to deal with the fact that this was happening. Life was a force in the universe that had managed to appear somewhere else. Because if you get two, there's no reason. Now you got to start thinking the universe is full of life, right? So I think it would be profound. Now, after, there's obviously a certain limit to what you can do with this, right? So I think, it's not like human beings would suddenly become super peaceful and we'd all live, lovely lives. We'd still be people, right? It's not going to transform. We'd probably still have wars and such, but it would really, really fundamentally alter how we think of ourselves. And then, of course, what's going to happen is we're going to start sending probes. If it's 10 light years away, you can bet we're going to start figuring out how to send probes at it. And which is interesting to think about whether or not people have sent probes at us. That's one place where you can sort of, is there stuff lying around in the universe because Earth has had biosignatures for billions of years. Yeah. Did somebody throw something at us? Right. And that's, a place where I don't, the UFO stuff, but is there stuff in the solar system? That's something you should think about.
Yeah. We had a talk with Paul Davies and Greg Benford right before the pandemic, and they talked about lurkers. Perhaps it's, there's something on the moon or on one of these Trojan asteroid belts. But the reason I asked, the prefatory question to Nuno's question about them avoiding us because we're too violent, in my impression, if you go down to the beach here in San Diego and you scoop up some water, there's trillions and trillions and trillions of examples of life. And we're pretty good at exterminating a lot of that life, including advanced life, bonobos and orangutans and so forth, as Jane Goodall, winner of the Templeton Prize this year, has documented. And, so I feel no necessary difference would really persist if we knew about it. In other words, if you found the exact same type of life on Mars and, Perseverance digs up a rock and there's all of a sudden there's a slime mold that I just, washed out from my coffee cup. I don't know if the world would act differently, but the question Nuno's asking is, are they staying away because they see the first signatures of advanced technology being, radar being used to track Nazi warplanes in World War II.
Yeah.
And then immediately afterwards, they see this huge flash of gamma rays from the detonation of atomic weapons. Maybe they're staying away because look, we're a violent civilization.
That is the plot of one of the most famous science fiction movies ever made. What is it? The Day the Earth Stood Still. Nice. I mean, it's possible. I tend to, I try and stay away from alien sociology, right? About how they would think. Like I said, I just can't even begin to imagine how I have no guardrails. I have no bumper rails for thinking how an alien society, are they capitalist? Are they communist? Are they, I just don't, there's nothing that science gives me that can help me sort of, say like, well, that's unreasonable or that's reasonable. Whereas like, for physics, chemistry, and even some basic biology, I feel like, I've got some things. So it's possible. But again, I will also, now let's enter science. Because what I feel like is anytime we do that, we're just telling science fiction stories, which is cool. Yeah. But I would imagine that any civilization that could travel between the stars, like, would not really worry very much about our puny weapons. So, that's, they would be so advanced that they would be like, to our little nuclear weapons.
So if you have time for a couple more questions, Adam, there are some good ones in here. So there's one on the stellar astrophysics front. In your wave model, do you account for feedback, supernovae, star formation rate of its own, planetary nucleation, agglomeration? Do you account for how much astrophysics is going into that versus, not predator prey, but expansion and differential equations of the typical, exponential growth curves?
Right. Well, like I said, that's an agent-based model. I mean, this is one of the interesting, this is a whole thing we could talk about the difference between, simulating via partial differential equations and agent-based models. And totally, I mean, it's fascinating to me because I'm also interested in modeling, societies and civilizations themselves. And this offers a whole new tool. It's a real galaxy model. We included supernova. We allowed regions to sort of sterilize. We didn't do things like star formation rates because we didn't see really how that mattered as much. But certainly, like, gamma ray bursts can sterilize regions of the galaxy. But what we found is it just didn't matter. Like, you'd sterilize a region for a while, and then you'd be able to, unless there's no reason, it's not going to be sterilized forever, right? After a while, you wipe out all life in a 300 parsec bubble, and then eventually, that could be refilled. And I was surprised because, look, I was looking for a way to stop that wave, stop the wave. So this, it's a great example of science where I had to be like, okay, I was wrong. There was just no way to stop the wave. But we did find what was cool was that the steady state offered you ways out of, and that just again shows you how beautiful science is, and also how smart Jonathan Carroll is, my longtime former graduate student, now longtime collaborator. Because he was the one who saw, like, wait a minute, it's not just the wave, it's what happens after the wave, propagates. So there are ways you can there are regions of parameter space where that steady state has big voids that are not being colonized. As long as you have finite lifetime for the civilization.
Right. Well, Adam, we are getting an alien message from a distant alien intelligence saying, please subscribe to this channel and exercise your right to vote with your thumb and your finger. And we are the only species we know that has this external opposable thumbs. Please read and buy Adam's book, which I have loved since before I even knew that we would be co-authors in the same stable, and hopefully have a new book coming out. You're talking about maybe this fall or later, and then maybe even an after book, some of which you may have shown my listeners in an early expose. So I really appreciate you, Adam. I love this book. You can still enter the competition, folks out there. You can still enter the competition to win a copy of it. Unfortunately, I can't send it out of the United States. UCSD postal regulations will shut me down. That crusty old dean. No, my dean is great. I love my dean. But I want to thank you on behalf of Eric Veary, the director of the Arthur C. Clarke Center for Human Imagination here at the University of California, San Diego, Patrick Coleman, Stuart Volkow, and all of us here at the Clarke Center. And I also want to thank you on behalf of all my listeners on Brian Keating YouTube channel. We'll put this on the Clarke Center YouTube channel. But please, we're trying to grow the audience, so share it with your friends. This afternoon, today, which is Wednesday, June 16th, 2021, we're going to have at 5 o'clock Pacific time, a lively, cordial debate between Eric Weinstein and Michael Shermer, kind of taking pro and con views of these alien unidentified phenomena, whether it's adversarial, military, with domestic, et cetera, or if it's actual technology, or if it's just confirmation bias. And it's just something that we want to see. I'm just kind of being the neutral moderator, and that will probably be my last bit of alien content for some time. I have to move on to other topics, but we do have an amazing audience, and that is coming later on today. So make sure you hit the notification bell, subscribe, and leave a like and a comment. Adam, thank you so much. It's such a joy to meet you. I hope to meet you in person, and I'm going to try to get you out here one year for Comic-Con. This year, I think it's virtual, but we're going to have the Comic-Con Museum here in Balboa Park, San Diego, and I want you to be there.
Excellent. Thank you, Brian. It was
Thank
great.
you, my friend. It's great. Everybody have a wonderful rest of your day.